All right, so today we have Craig is going to be talking about VIM, which is not macros. It's
Malleable VI.
Malleable VIs. We both got yelled at by the LabVIEW champions of how dare we put the wrong name out there.
I wrote a title and an abstract in about 5 minutes. I sent it off months ago, forgot about it, and then got in trouble for it this week.
Yeah.
Great.
Yeah. So anyway, so just so you know, the only place where VI macros belong is on the actual extension, VIM, but they are known as malleable VIs.
Yeah, I'll call them malleable VIs and VIMs. I don't know if the other people call them VIMs, but it's like a quick
way to,
version I'm calling it.
There you go. Then we're going to get in trouble because of that.
Darren is shaking his head.
Do you have a better name for it before I start saying that all the time here?
Malleable.
Malleable. That's such a word sandwich. It's so long.
If you just keep saying it over and over.
I would love a sandwich right now.
It's shorter than polymorphic VI, so there you go.
If I
VIM too. VIM is fine. Malleable VI is fine.
But not VIM?
I don't like that.
That's a personal problem. That's not like an objection outright. So.
All right. And then as soon as I get settled, I'll connect to the meeting, and then if anybody has questions in the audience, I'll relay them to Craig. And then after Craig is done, we'll take a 5-10 minute break, depending on what time it is, and Aaron is going to be talking about
architecting.
Yeah.
If food shows up, we'll just pause.
Yes.
There's no reason to wait for it to get So,
they wanted to call you back. Like, no, we can hold.
There's been a lot of presentations about malleable VIs. Who has seen these presentations at NA Week or other places? So a few people. For those of you that have seen those presentations, has anyone used malleable VIs? So like 20% of people. Okay. That's great. Most of the presentations I've seen on this talk about malleable VIs from the perspective of here's all the features they let you do. And today I'm going to try to talk about malleable VIs from the perspective of here's how I used them in a reference library, and then I'll talk about how the features under the hood allowed that to happen. So to give you understanding here, I need to go with some background, and just to give you context about where I'm personally using them, doesn't really matter. I'm going to try to go through this relatively quickly because this just to help you understand the case that I'm using it in. So I do a lot of work with semiconductor test systems. Has anyone used these? I'm expecting probably not. A few people, a little bit. It's basically a PXI controller and a big tester connected to a DUT. That's pretty much all it is. You got a lot of PXI modular instruments, DAC cards, DC power, SMUs, all sorts of digital instrumentation, stuff like that. And we have some plugins and software to make this easier. Specifically, we use TestStand Semiconductor Module, which is an add-on to TestStand. It does things like pin programming, multi-site abstraction binning, handler reporting up, all this stuff. Basically, for those of you that have used TestStand, it looks just like TestStand. In the TSM paradigm, you initialize your instruments in the process setup, callback, and you clean up the sessions in process cleanup. Okay, so this is just normal TestStand. We're initializing things, we're closing things down at the end. And if we look at actual test code, it might look like something like this. Okay, so in TSM fashion, we call out a pin. Our pin in this case is VDD. It's some sort of voltage supply for our DUT. We call pins to sessions. We configure these things. We do some stuff with them, and then we measure and we push data back to TestStand. So I would say if you guys have used application interfaces or APIs or programmed in LabVIEW, this should look almost identical to what you do regardless of where you're coming from. So even though I'm underneath TestStand Semiconductor Module on a PXI, this should be very familiar. The difference really is instead of calling your instrument, you're calling this a pin and doing this stuff. And for the context of this presentation, I'll be talking about these VIs here, these reference library VIs that we've created to make things a little easier when you're programming these testers. So, questions so far? Who can tell me what this is doing just from the pictures? Yeah?
Looks like you're just doing a power measurement.
Yeah. Exactly. I'm configuring the sessions. I'm sourcing a voltage. So I'm saying I want to put 10 millivolts onto VDD with a 1 milliamp current limit, which is stupid low. I'll wait for that to finish sourcing, and I'll take a voltage measurement back. So just like all hopefully good APIs, just by looking at this, you kind of get a sense for what it's doing. Going into this very specifically, pins to sessions is using a semiconductor module function to get the actual instruments that are connected to that pin. We configure the settings. In this case, we're setting how long it'll be for each measurement. So we'll have 1 millisecond per measurement. We will source the voltage onto those pins so that they'll be at 10 millivolts. We'll wait for source complete. For any of you that have used DC power, this is a very common thing to do for an SMU. And then we'll take a measurement, just as I said. Cool. Now, these functions have a .vi extension, but these functions have a .vim extension. And just from what you see here, there's nothing about this VI or this test that you look at that lets you know that it's a .vim or a .vi. From the user's perspective that's running test code, you're just interfacing with a reference library and calling the appropriate functions that you need. So from this level, the user doesn't care if it's a .vi or a .vim. But we care about the .vim, so let's look at those. The primary use case, the primary reason why this source voltage VI is malleable is to allow input type flexibility. And specifically, talking about here is, sometimes I might want that type to be a single element, like in this case, where I want to source 10 millivolts on it. Or sometimes I might want to use an array instead. So notice that in this example, I'm getting sessions for pins A and pin B. So there's two actual physical pins on the DUT in that case. And in some cases in my test code, I might want to put 10 millivolts on both of them. So when I call source voltage with just a single scalar input, I'm sourcing 10 millivolts on both of them. That's how this API is working. However, with the same malleable VI, if I connect an array up into it instead, and I specify two values, this now will actually correlate. So 10 millivolts will show up on A and 20 millivolts will show up on B. So it gives my interface a little bit more power than I would have otherwise had. And you'll notice I'm only connecting two of these inputs. So the required ones are voltage level and current limit, but I have some recommended inputs in case you want to be more specific about what ranges on the instrument are going to be used. And if you actually think about how many different combinations happen here, each of these inputs is malleable in terms of scalar to array. So I could have this case, which is two scalars. I could have this case, which is an array and a scalar. I could have this case, which is two arrays. And I can have all additional combinations for these limits, or these ranges as well. So that's actually 16 different instances that one VI is handling. So a colleague of mine had to backport this malleable VI back to 2016 LabVIEW, which didn't have malleable VIs. And because of that, he's had to create 16 instances to cover the same functionality that we get here, just by the malleability of the VI allowing it to be a scalar or an array. Because it's for 2 to the 4th power different combinations of those inputs being scalars or arrays. So this is the first point that I have, is that previously you could kind of do the same thing as malleable VIs with polymorphic VIs, but you'd have to define the main VI for it, and then that would link to all the specific polymorphic instances that it would work on. Who's used polymorphic or created polymorphic VIs? Yeah? So
we see you there every second of having to do it.
It's not the most fun. And I think if you're able to use, by 2018, well, technically malleable VIs are in 2017, but you try to push to the newest version possible. The newest patch, version 2, 2018 FQ1, F3 even has some better behaviors here. Anyway.
2019, great.
2019 even better, yeah. So switch to 2019 if you want to use these. But if you've created polymorphic VIs in the past, malleable VIs could make your life easier. There are some cases where you can't address the needs of the polymorphic with the malleable, but in this case, where I can just manually hook up whatever I want in terms of elements or single elements or arrays, it worked perfect for what I needed. But any questions so far? Any background I'm missing yet?
The thought that's going through my head is, one, is this helping avoid errors or not? I can see that if I just had the scalar version and the array version, even just if I were also backporting this to 2016, I would have not created 16 versions.
You probably don't need all 16. Like, who actually needs every mix?
Well, I could just say, if I'm going to use an array input on voltage level, I'm going to use an array input on all the inputs. And it's going to force me, if I've got 2 pins that I'm activating, that I'm always going to make sure that I have 2 inputs for every, or 2 values in the array for every input.
So yeah, that gets into a little bit of a difficult programming challenge, because these are actually indexed into a for loop inside with multiple indexing tunnels. And one of the problems is if those arrays are different sizes, you might not do the source on all the things because of how it ends up mapping the session.
Well, where's the bug in the program, right? The bug in the program.
Yeah.
The bug could also be that I have a 20 instead of a 20M in there in the voltage level, and I'm suddenly putting out 20 volts.
Well, and it would either error because it's out of range, or it would blow up your duct because it can do that and you don't know, or, yeah.
So I just, to be able to, I guess I'm not convinced that you really needed 16 combinations of things. You maybe could have just done the scalar version and the array version, and you might have been easier for a novice to avoid these things.
Right. So I think my point here is I created the Malleable VI version of this to begin with because there were specific cases where I wanted this instance here. I just wanted an array of voltages. I actually don't really ever care to have an array of current limit ranges that often, almost ever. There might be a situation where you do. Because of how the Malleable VI is implemented, I get it all for free. So I agree. If you were to go back to Polymorphic, maybe you just have a version that's, array input for the voltage level, and that's enough. Or maybe you have one that's arrays for both. Yeah.
Say it another way. It's like, say I have a thin C that I suddenly add, then
it'll throw you
visit everything and actually pay attention to it and do it consciously as opposed to, let's just solve problems.
It'll actually throw an error if the arrays don't map correctly, if they're different sizes. And it does its best with the array sizes, but sometimes it gets a little weird. And I'm not going to go into that because it's more TSM semiconductor module, funny business, but yeah. All right, so any other questions before we see a little bit about how this is done? Do you guys see this as being useful if you ever need to use Malleable VIs? Yeah, maybe. Sometimes. As with any feature, use it when appropriate, and don't if not. Okay, so what does a source voltage VI look like? Well, it has the 4 inputs, and it has also a VI in. So this Malleable VI is calling a expand array Malleable VI, which are 4 different instances of it, of the same VI, and a normal VI. And I'll talk about this a little bit more later, but it's actually a really important point here that I am actually calling another sub-VI in this Malleable VI very intentionally, because I don't want to have too much stuff that's complex getting inlined. So if you look inside that expand array function, this is the case that's being compiled into that. So in the case that you provide a single element, that element just gets initialized into an array across all the pins that we have. So looking here, it's basically just initializing an array of the appropriate size that gets passed to this all-array version of source voltage. And because they all do the same logic, it makes sure that each array is the same correct size according to how many pins are actually in that list. Cool. Does that explain a little bit about how this works? Any questions? Not going too fast. Does anyone hate this yet? I only kind of hate it, which is about as much as I can expect from my own code. There's another case here. So this structure is called a type specialization structure. It's basically the case structure for malleable VIs. I'm not going to go too much in depth about this. I would actually, if you're looking into this stuff, there's a bunch of great presentations talking about all the ways to build malleable VIs. In this case, so we're going from the 0 to the 1 case. You can see how the input for the 0 is a scalar, and the input for the second case here is an array. So basically what happens is LabVIEW at compile time figures out, is this an array input or is this a scalar input, and it chooses that path through this mapping function for what gets called. So if all the way back here, in this case, this top wire is going through that mapping function and it takes the array version of it, and the scalar one is going through that mapping function and it takes the just generate an array case of it. Okay? Yes?
Lock you to pre-allocated.
It locks you to inlining, which I'll talk about in a moment. Very good point. So malleable VIs have to be inlined. Who has used inlining before? Who likes it? Who inlines everything? That's great. Nobody should inline everything. This kind of comes into a discussion of, like, to really understand this, you have to know why you choose reentrancy settings. And you have to be very intentional with what reentrancy settings you do choose. Malleable VIs have to be inlined by definition. So let's talk about inlining. Well, when you inline a VI, what you're actually doing is making it as if it wasn't a sub-VI at all. That code was just copied straight to that calling diagram, and it just exists there, and it's compiled in line. So there's no sub-VI wall, there's no corrector pane, there's no nothing. It's just sitting right there. And so this malleable VI has two steps of inlining inside it, because we have source voltage malleable VI that's directly inlined into that. So this is just basically copied there. And then each of the expand array functions get copied into these places here. So from the perspective of the top-level diagram, it gets this and that just pasted straight in. Okay? But remember, this function is just a normal VI, and it's not inlined. So the only code that actually gets compiled in that's actually complex, but it's not really that complex, are these expand functions. Okay, so who has seen this compiled code complexity metric? Who has seen the gigantic VI that takes a minute to compile because you move something? Yeah. There's a link between how long it takes to compile something and the compiled code complexity. So a really important point here is that whenever you're dealing with inlining or just VIs that are gigantic, the thing that makes developing them hard usually comes back to the compiled code complexity of that VI. So in this case, looking at this example we've been looking at the whole time, the compiled code complexity of this is quite low. And I have a general sense for these numbers and these ranges. A top-level VI usually has a couple numbers there, like 2 to 4. A simple VI should be well below 1. A complex VI that takes a long time to compile can be 10 or higher. So this number directly tells you, like, what is my editor experience like with the VI? And everything that you get inlined into your caller is adding code that has to be directly aligned. So if you inline your whole application, you're effectively programming compiler-wise as if everything was on one diagram and everything takes a huge amount of time to compile. So when I was talking about this VI here is not inlined, what I'm trying to say is that this VI contains complex code, and I don't want that to be having to be compiled everywhere I use this function. I only want to compile the minimum set of operations, complexity-wise, as necessary to make my malleable VI work. And I want to quickly exit that region into normal VI space again so that I don't have to have the entire tree recompile. Is that making sense? I have a demo here that will help hopefully pull this together. But, yes.
So the sub-VI, case 0 helps more code, case 1 is quite a bit of code?
Yes.
Why did you elect to leave it there as opposed to create a sub-VI for that chunk of code? Yes, initiated 4 times.
It gets inlined, and it would have to be malleable as well, because I'm doing type propagation on that as well, which we'll talk about later. This isn't always double. So if I made it a subVI, it would just be an inline subVI anyway, because it has to be malleable as well. So, but we'll talk about them in a bit. But yeah, a point here that I skipped over is that when you're doing malleable VIs, the cases in these type specialization structures that don't get accepted. So in this case, because we're mapping a scalar to an array, the next case here is actually compiled out. It gets completely removed. It doesn't physically exist in the compiled path. This is called dead code elimination. This is something that LabVIEW does if you turn off debugging and enable optimizations anyway. And the inlining process, which is also part of malleable VIs, removes these other cases. So it's a compile time choice that LabVIEW is making. If you're doing source code control, who does source code control? Everybody? Yeah. One brave soul. If you're doing source code control and you're using these malleable VIs or just inline VIs in general in your application, you also have to keep in mind that if you change logic in that sub-VI, you're actually dirty dotting all the callers, because all of the callers of that sub-VI are directly compiling that code as part of their VI. So as opposed to, like normally you can change a sub-VI as long as the connector pane is the same. Even if you've changed the logic, the caller doesn't change. It doesn't have to be recompiled or saved. But the second you're calling inline things, that's just code on your diagram to begin with. So there's a little bit more pain when calling inline things in general. Yes?
So are you using source code control without separating compiled code?
Yes.
Okay. It's worth clarifying, if you separate compiled code, it does not trigger upstream recompiles.
That's true, because the .vi doesn't have to be resaved. That's true. In this case, we're sitting under test stand, and for deployment reasons, it ends up being simpler to pretty much always leave them compiled code included, as painful as it is. One day, it will probably be easier to not have to do that, but like you can make a build process that goes through all your VIs and checks that box, so you can actually have it separate. But anyway, for our purposes, we often leave that compiled code included just for runtime engine behavior performance and test stand. That's another kind of side note to this. Other questions? Comments?
No, dirty dots and with separated code compiled.
Yeah, because it's a compiler. It's like basically the compiled version of this has changed because the sub-VI changed, but that's inlined. So, but if the compiled code isn't part of the .vi file, it doesn't dirty that.
Do you mark the separation on a case-by-case basis, or do you just don't separate for the entire project?
I've heard people say different things about this. I think if you're using source code control, marking separate compiled code from source, so it's not in the file, is nice, because it means you have less changes to your source code.
But what I'm saying is, when you say that you're not separating for these changes, are you just doing it for the entire project or just for the VI?
We're not separating because of test stand and unrelated reasons.
Oh, okay.
I would say you should separate compiled code from source for, as much as you can, unless you find a good reason not to. And we have a special case where we don't because of an annoyingly good reason. Yeah. Other things, yeah. We do a lot of things under test stand and test stand send acceptor module that initially strike you as not great style, but then there's reasons for it, and I can't escape those reasons. So yeah. Okay. Let's do a demo about code complexity, because I think this is a pretty cool topic that I can do from scratch. So if I have a blank VF here, and I put a for loop down, I put a random number generator, and I put a constant here, 16. I copy this out, and I make an indicator, run this VI. I now have a VI that creates 16 random values, and I can look at the compiled code complexity of this in VI properties. So memory usage, compiled code complexity. Point 1, it's very, very non-complex. And one of the pieces that we use in these libraries a lot is parallel for loops. And that's the quickest way I have found to blow up the compiled code complexity of a VI. So normally to get something very complex, you have to drop a lot of nodes, you have to connect a lot of wires, you have to make something massive to see this. But if you have a parallel for loop, who's actually used parallel for loops? Do you like them?
Well, I didn't know about this problem.
You need to be really careful with using parallel for loops. A lot of people just use them improperly, and that's a whole different topic.
There are places, when you are doing optimization, there are places where you have.
There are absolute places where you do, but they are very specific, and you should know when. You should never do them unless you've benchmarked it and you know it's necessary, because sometimes it actually slows everything down. Okay, so right now, normal for loop, 0.1, okay? If I parallelize this for loop for 16 instances, which won't even be for this computer, but whatever you choose in this pop-up, this dialog is what LabVIEW compiles in the binary. Whether or not it actually can use that many instances is a different question, and again, that's past the scope of this. But just changing that one setting for this for loop and running this again, it still works, right? It still generates all my values. If I look at the compiled code complexity, all of a sudden we're at 1.1. So, you know, this might even be a whole main VI complexity. Okay, let's make this a sub-VI, because as ever, we're talking about malleable vis, we're talking about inlining and trying to understand how this makes your editor behave. Connect this indicator, make a new VI, put this over here. I will call this VI in this other VI. I'll make an indicator here. So now if I run this VI, I'm just calling it as a sub-VI and showing the values. Now, if I look at the compiled code complexity of this VI, it's back to 0.1, because I'm calling a sub-VI that is non-reentrant by default, right? And I don't have to recompile that as part of my caller. I'm just jumping over that other function and it's executing. So this compiled code complexity over here is high, but that's fine, it's a sub-VI. And the compiled complexity over here is low. And if I do this a bunch of times and run it, you know, it still stays pretty low. Now, this is where this is where you start looking at inlining. So if I set this to inlined, like this is the main checkbox you have to enable is this one here for inlining in the VI properties. And then I run my caller, you'll notice all of a sudden my compiled code complexity now mirrors that sub-VI because it's being pulled in and compiled in place. And this is where you see pain, because when you're calling sub-VI, you don't call them just once. You call them throughout your test. You call them all sorts of places. And then I run this, and my compiled code complexity is 4. It goes up and up and up. And where you start seeing this really cause pain is if you have something really complex, like a parallel for loop and a parallel for loop. Never do this. But this is another example of how to blow things up. I don't want conditional. And then when I hit run here, notice it actually wasn't bad. It's only 7.1 complex, okay? But if I run over here, I hit run, I use the shortcut, and it's just hanging. So like I can't. So and this is the behavior you see for large VIs that don't have proper sub-VI creation, don't have proper reentry settings, are trying to do too much. And this is just a really simple way to demonstrate that behavior. So if I control click this, it forces a recompile, and I click it, it's frozen now, and it takes a good 10 seconds to actually go through and compile that. Now, you should never do a parallel for loop and a parallel for loop, please. That's just bad. But at least demonstrates the issue with complex code. So if you want to use malleable VIs, they have to be inlined. But if you're inlining things into your callers, and those things are complex, you are making a bad editor experience for your users. So try to... What?
Complexity.
Oh, yeah. You want to see it? 14. That's no big deal. Let's just blow this up even more. Go to 32. Anyway, it just gets really ridiculous. For any VI that takes minutes, you can just pull that metric up once it's compiled, and it'll be some crazy high number. So that's also another way, if you ever get a slow VI, to figure out why is it, like, where am I in this complexity, and you can actually use that as a metric to figure out how to make it more responsive, because you can chase down that complexity and do it. But I'm just sitting here, compiling away, chugging on the CPU, trying to compile this VI. Anyway. Questions about demo that help talk about compiled complexity and why you might care? I mean, you care because it's inlined, and whenever you inline things, you are making things more complex of the caller diagram. Okay. So, if we look at our demo VI that we were looking at here, this simple usage, the compiled code complexity of the top level VI is very low, 0.2. This malleable VI we've been talking about is also going to be very simple, 0.2. And then if we go into the actual function that sources the voltage, it's 2.4. So I'm hiding the complexity of this source voltage subVI in a normal shared clone reentrant subVI. That's what I'm trying to keep. If this was inlined, it would make all my users very mad at me because you'd move stuff around, you'd add stuff, and it would take forever to use. So, there you go. And it does funny business with parallel for loops for other reasons that I'm not going to talk about here, so I don't have time. But if you parallelize a for loop, it takes time to actually enter the for loop, which is potentially slower if you don't have that many sessions. Okay, back to the presentation. So, in summary, for the compiled code part, if you're designing your subVIs or your reference libraries correctly, you should be thinking about compiled code complexity. And normally this isn't a problem because you're not using inlining, but the second you start using malleable VIs, it's something to think about. You want anybody that's using your VIs to not have a bad editor experience. And in general, you should be aware of and intentional about the reentrancy settings of your VIs. The default non-reentrant is great for debugging. It's required for something like a functional global variable. But if you ever have a case where you have to call the VI twice in two places and you want them both to execute, you have to use one of the shared clone or pre-allocated clone versions. And then if you want to do some performance-related things or use malleable VIs, you have to do inlining. And that has some benefits as well as some editor drawbacks depending on how you're using it. So, yes?
In reentrancy, I define matters and beyond doing LabVIEW.
It gets, so if you have a VI, TestN cannot call an inline VI, or I can't call a malleable VI, one of the two. So often the test code you're calling is one of these top two reentrancy settings, either non-reentrant or shared clone. And then since the inline code is part of that compiled object, it's just calling that VI as normal. It doesn't care. So normally these malleable VIs, these inline things are towards the bottom of your application stack. They're kind of the worker functions that you have in your library. Any views on food?
No, because I'm 1 minute. My stomach is kind of fine.
All right. All right. The other thing that malleable VIs let you do is flexible input types. So another VI here that has been in this example the whole time is this configure settings VI. And so far we had it configured just for aperture time and source delay. But maybe I want a different transient response setting. This is a DC power source measure unit feature for an instrument. If you don't know what this is, don't worry. I'm just configuring a different setting on each channel of the instrument. And I want pin A to be normal transient response, and I want pin B to be fast transient response. You can see how this is actually a type def enum. And you can see how the type into the malleable VI is just a type def enum. And we have the same behavior that we talked about initially with the levels where that can be a single element or an array because of malleability. But if you look into that VI, you'll notice I'm using the same expand array function. So this type, again, these are VI, malleable VIs, and this is just a VI. If you look at this type, it's an integer. If you look at this type, it's an enum, type def enum. If you look at this type, it's a double. If you look at this type, it's an integer again. Malleable VIs change our expectation of the static typeness of LabVIEW. So who knows what static typing is? Hopefully everybody. When you call a subVI, the type on that object, that connector pane, is the type you have to connect or your wire breaks. Well, malleable VIs do that dynamically. They're not just inline, but they let that wire type propagate through the VI. So whatever's on your front panel is your malleable VI doesn't necessarily force you to use that exact type. So we've already seen the double case where it makes a double into an array, but this exact same expand function also works for all these other types, because the expansion we're doing is it's not type specific. We're just indexing an array or building an array of that type. That type can propagate across this wire through the expand function, no problem, regardless of what type it is, as long as it's either a single element, a scalar, or an array. And this is the case I think most people see for malleable VIs. Data manipulation things that have to happen on different data types where the logic on that path is just array, reshaping, indexing, resizing, but it's not type specific. And historically in LabVIEW, you were locked down to whatever type you have in your front panel, whereas when you make it malleable, it'll actually type prop through as part of that inlining process. Okay, so same VI, the other source voltage one, except now we're propagating both the other types as well. And if you start thinking about how this would blow up, how many polymorphic instances you'd have to make, it really gets worse, because this expand function is anything. Like, you'd have to make every data type version of it for all that flexibility, whereas malleable VIs just give that to you out of the box.
But in general, like if you're doing a polymorphic VI, you don't go out of the box and say, I'm going to make every possible...
Yes. But you're always chased by that. Oh, I need to add this one. Oh, I need to add this one. Oh, I need to add this one. So yeah, you have to make a specific choice about what subset am I going to support.
Yeah. So basically, because the idea you had at the beginning is I have 6 DIMs, so obviously I need a DIM. But it might be that malleable VI. Sorry, guys. But it might be that okay, I have 2, but still I'm going to bite the bullet and start with malleable VI.
Yeah.
And then I end up just having. So where do you draw the line of forget polymorphic, go malleable?
I hate polymorphic. I just hate making them. So I think VIMs have a better purpose underneath your applications as subVI. So like this example here, I happen to be using VIMs at the actual level where users will interact. But I find them more useful in the subVI layer as workers underneath my code. Because it's easier to handle if it's just dependencies of my stuff, not the top level functions for the stuff. Yeah.
To add on that, so a use case that we found that you could be pretty effective, like use of time propagation when you're wrapping a driver level polymorphic VI.
Yes.
Auto choice.
I'll get there.
Yeah.
I'll get there.
Have you gotten there yet?
Not yet. Very soon. So hold that thought. But yeah, the propagation happens into the polymorphic VIs of a malleable VI, if you're calling a poly and a malleable. Yeah. So I do have to mention this because auto choice. I think I'm looking. This is part of the palette. So if you go to comparison, assert type, this is the new palette that you'll see for versions of LabVIEW that have malleable VIs. And most of these are, the type specialization structure is kind of the case structure for malleable VIs. The rest of these are mostly about forcing a certain type. So a lot of the logic and the way you build these is, if my type is this, I want to do this. And you force that by saying, I want to make sure the incoming type is a certain thing. I don't really have time to talk about this. There's a ton of good presentations on about all these different features and how to use them. But this is the palette you can look at with chips with LabVIEW you can use. That's there. And another important point here, I think I only have a few minutes left, but debugging these VIs. So for those of you that have used inline VIs, one of the pain points you probably know of is that they're not debuggable. Like if you enable debugging, you get this little yellow checkbox and you break your VI because it says you cannot enable debugging on inline VIs. And since malleable VIs have to be inlined, you cannot debug malleable VIs directly. Now, there's this cool little thing I found today. I wish I'd known about before, but I was just exploring. Like, how do you normally debug these things? Well, you can actually right-click on it and convert instance to standard VI, which will actually make that a sub-VI call of the actual specific instance that you're using. So if you're doing different types and different things, it'll give you a nice version. So debugging-wise, that's a cool tip. You also can just...
Does it go both directions? Or do you have to, once you convert to a standard VI, you have to go look at...
You'd have to undo it, but it lets you debug. So like if I have...
So it doesn't go both directions, just the undoing.
Yeah, so like if you have this here, if I open up this, it's just a malleable VI. But if I actually more specifically, let me look at my other example because it'll be more interesting. This is the array when we were looking through there. If I right-click on this and say convert instance to standard VI, I see something different than if I just double-click on it. If I double-click on it, I just see the scalar. It doesn't tell me this is the specific one you're doing. But if you right-click on it and say convert instance to standard VI, it says I'm going to convert it to a standard VI, and it's not going to be linked to the malleable VI, it's going to be a new sub VI. And I open that up. Notice how these now appear as arrays, and you can see actually how that's propagating through this VS. So now it's easier to debug. And I have a couple examples later that are even clearer for this. That when you are changing the type or whatever, it can make it a little bit nicer. Does that finish the question for that? Okay. This is an example which...
You didn't undo, by the way. So
what?
Just so you remember, you did not undo the conversion.
That's fine.
Source code.
This isn't source code controlled, please. I built this today. Come on. Let's be real. So this is an example of another function we made a malleable VI for. TSM Semiconductor module, when you're publishing data back to test stand, there's a polymorphic VI, which has a lot of options for it. So let me just demonstrate this for you, because I don't have much time. But digital TSM publish. This is a polymorphic VI with a bunch of different choices in it. And as you change your inputs to your function, you might want different publishes. So, like in this case, if I'm publishing 1D data, I want to do a certain type of mapping. If I'm publishing 2D data, I want to do a different type of mapping. And as I change these front panel inputs, the malleable VI figures out which case will actually compile. So this is kind of another debugging tip. These front panel objects you can rename or change to the types that you actually expect to have passed through. So here I'm going double to Boolean. And you can see the polymorphic VI that I'm calling is also changing double to a different type. So if you're calling polymorphics, you can still use malleable VIs, and in my experience, it seems to work. This kind of scared me at first, because I'm like, that seems crazy, but cool, so I'll use it. So I haven't found too many drawbacks here yet, but yeah, this is an example of 2D Boolean, and then you can also do 1D Boolean, and I'm using the specific feature over here to make sure that I'm only ever allowed to hook up a Boolean into this or a double into this. And if I do anything else, if this is a integer, the whole thing breaks because I don't have a valid type, the type specialization structure. So yeah, you can call polymorphic VIs. And the interesting part here is, the reason we had to add this is that if you don't have this here, and you connect it through, because the polymorphic VI can coerce the numeric type, you get coercion in an executable thing. But I'm passing in a data type which my publish doesn't natively force. So by doing a structure here that forces it to be either an exact double or an exact Boolean, I make sure that I only will work if I have those data types coming in to the malleable VI. So this is where you start getting into, when you use these specific assert structural type match functions or the type specialization structure when building malleable VIs, because you can force. I always know this wire has to be the data type. Okay, that's how you make it. Questions? Yes?
LabVIEW smart enough to compile that out of the runtime code?
Yes. Yeah, it's just nuked. It's a compile time choice, but it doesn't physically. A lot of like this function here is one of the ones, assert array dimension count. I love this one. These are natively implemented. It's actually very hard to assert that they're the same size, so you have to be either, are they 1D or arrays, or 5D or 4D or 3D or 2D? And apparently 6D was not a worry. Yeah, these built-in malleable VIs are pretty cool because all they're doing is the only things that were added to enable this are the .vim extension, this type specialization structure, and the assert that I can think of. This is structural type match. And then all of the actual palette items, just build those into useful blocks that you can use. So here, I'm making sure that this case only works for 2-dimensional arrays, and this case only works for 1-dimensional. So I wanted to do different things based on those things. There's also a function in here that is doing a lookup table. And it's a fairly simple lookup table. It's just array operations. It just replace array subset with different mixes of clusters and indexing and stuff in there. Yes, Malleable Vis ship with LabVIEW. You go to, I'm answering a question on the thing because I saw it, but it's under comparison. I never use the palette, I forget.
Array.
They're all here.
There's also an array, 2D sort or something.
Yes, a lot of the new functions actually use malleability because it makes it easy. You can actually have dynamic typing like a lot of the primitives have. But we have a lookup function that's basically just reshaping one array into another size that we use in a lot of places. And again, we're using the dynamic 1D, 2D arrays in different clusters, and all these different cases have different things. And if you look at that here, you can see different cases of where this lookup table function is called. So the one down on the right is the one we've talked about a little bit in terms of publishing. In this case, you can see it's passing a double through it, a 2D double to a 2D double. But up here, we're using that same function for a 1D to 1D with a different cluster. And then here, we're doing 2D to 2D with a different thing. And here, and it's integers, and this one's double. So this one function encapsulates a bunch of different reshaping operations that end up being, in my mind, collapsed into the same type of logic. If I just want to do a lookup table from one order to another, and I was able to cram them all into one VI. Retrospectively, maybe I should have used more VIs. It's a little confusing, but this is all sub-VIs of this reference design. So really, the only people that have to care are people that have to maintain it, so me, and any other poor soul that has to help me. So, yeah.
When you leave.
Like Danielle. So. Yeah. Anyway, that's pretty much the time. Do you guys have any questions or any other stuff you want to ask about? Yeah. Do you have a question, Kyle?
Yeah, what's the flex? Publish function.
Was it published?
Yeah,
that's a good question. 0. Let me compile it. Sometimes when you check this, it's not compiled because you've been messing with it. Yeah, we got an error. Okay. 0.7. Fine. That's a good question because, as you're building these, I could have potentially put some of this into subVis. But this, actually, I don't know because this can't be this already is a subVi. I don't remember if this is inlined. It's not malleable, but it might be inlined. I did inline that. So yeah, that could maybe not be inlined. I don't know. But in my mind, 0.7 isn't the worst. If people complain about it, I can make it better. Yeah. Yeah. Questions?
When did the code complexity metric get into LabVIEW? I haven't noticed that before.
I think it's been there for a long time. I've only been here for 7 years. 2010? Okay. So before I started, barely. But.
You could query it, but it was never that useful earlier.
Yeah. I really didn't find it very useful until I started playing with Malleable Vis, and it really helped me understand, how I make decisions about inlining or not, or how I actually wrap my VI. Because, especially because I have so many parallel for loops. I don't want a parallel for loop to ever be inlined, because my users are going to hate me. So.
It's a good way of telling your customers that their code is in fact too big and having metrics attached to it.
Yeah.
People always get really defensive.
It's really hard to tell people the code is bad.
Yeah.
Everyone's
you have a number that says it's bad.
Your code is 40 on the complexity scale. I'm impressed. I just have 2 parallel for loops. What are you talking about?
So I was going to say a few things that everything that Craig just talked about with Malleable Vis. For those of you that don't know me, I'm Darren Attinger. I've been in my early for a long time. Malleable Vis were first added as a feature in 2017. They were actually an unofficial feature all the way back in LabVIEW 8.2, but don't use Malleable Vis before LabVIEW 2017. Jeff K snuck an X node into LabVIEW 8.2 that lets you rename a .vi file to .vim, and they would behave like you see. here.
Since 8.2, oh
So
gosh.
if you want to play around and have some fun, go for it, but don't use just case Xnode-based malleable VIs in any production code. Along those lines, they were introduced in 2017. We fixed a bunch of bugs in 2018. We fixed a bunch more bugs in 2019. So if you're planning on becoming a heavy malleable VI user, try to use the latest version, if at all possible. Is this 2019?
This is 2018.
Can you bring up the array palette? So one coding convention that I follow that I suggest other people follow as well. You see those slightly darker items on the palette? Those are all malleable VIs. That is the coding convention we and LabVIEW R&D have applied to any malleable VI that we ship. So I suggest doing something like this in your malleable VIs. I know if you didn't, that's fine.
I can do it now.
I find it handy when I'm looking at a diagram to know which things will adapt the input types. And poly VIs usually have that little ring that you can see when you know, oh, that's a poly VI. There's no distinguishing characteristic of a VIM other than hovering over it and seeing that its file extension is .vim. So if you follow a coding convention like making them all a little bit darker, like that color right there, then it's a lot easier to see in your VIs that you're using malleable interspersed with regular sub-VIs.
You have the RGB files.
I always open one of those and copy.
What? I will do this for you.
You don't have to open it. If you go to the block diagram and Control-C on the sub-VI, you can paste it directly in the icon.
Yeah, that'll copy the whole icon.
Yeah.
That's right. And then one other thing I was going to say, there was the question earlier about like malleable VI, poly VI. I should always use malleable VIs right now because poly VIs are crappy.
There's still a case for poly.
There's still a use case for poly, and that use case is when you're defining a mode of operation for a sub-VI. So all of these VIs that Craig showed in his demo have a commonality, and that is that they all behave exactly, they're all doing the same thing, you're just giving them a scalar or an array, they're still doing the same thing. If you have like generate waveform VI, and that VI can generate a sawtooth or a sine or a square, you're defining a mode of that thing. So malleable VI doesn't really make sense there. You're not.
The input types don't determine what you want out of it.
Yeah, then in that case, poly VIs are still really useful, and I include them for that use case. So I think that's all I was going to say.
Thank you. Question?
One side note I would add, we've talked about they're supported in 2017. Before 17 SP1, there was no type specialization structure officially on the palettes.
Please use 18 SP1 F3, please.
Yes, but if you have to use 17 and you want to use malleable for Vim, it's not the end of the world, but do use SP1.
Yeah.
You do not want to use 17.
I do have to mention one other thing. If you move your dependent malleable VIs on disk, you might have some pain relinking them that you can't resolve with the resolve conflicts window. So be aware if that happens. I think, as ever, we're still fixing things as we find them. But overall, I've been very happy with how much less code I've had to write because of them. So I'm okay with all these behaviors.
Also, did anybody notice when you right-click and did the convert option to turn it into a regular sub-VI? That might look familiar to you because that's what you do on an Express VI. And it turns out that the technology that facilitates Express VIs, which is called Instance VIs, that's the same technology we're using for VIs. That's why they have similar operation there in diagrams.
Bam. Woo.
File dialog Express VI, that's the one I use. I used to use time delay until I figure out that the error terminal does nothing.
I'm sorry.
The lapse time is also very useful.
Yeah.
Question? Comment? I'm not already, I have no idea. Oh, by the way, I'm an applications engineer. I used to be a system engineer. I do the same thing. It's okay. Don't worry.
We're all working.
I forgot to introduce that. So. That's it. That's all I got.